right? So we can actually just do that. So number of edges is less than or equal to v square, and so if you take the log of both sides, that tells you that log e and log v are of the same order, right? Because there's just a constant involved, and therefore the cost of each delete bin operation is log v, right? And the connectivity test, you can use what is called a disjoint set data structure, which is something that we will talk about much later in the course. So for the moment, you assume that it's the connectivity check can be done in log v time. Actually, it can be done even faster than that. But let's just assume that it can be done in log v time. And so for e iterations, we have a runtime of e log v, right? Could we improve this to say v log v? Is that something? Could we have done that? We are only adding, n minus 1 edges. Does this still have to be e? No? Okay, so how can we cannot or we can? We cannot, okay. So, well, naturally, right, because we don't know for whatever it is for, again, going back to the example, right? If let's say, right, these two edges were not there, right? Then the spanning tree requires that edge to be added, right? Which means that the highest cost edge needs to be added in order to get the spanning tree, right? So which means that you basically, because the highest cost edge is going to be the very last in your queue, therefore you really have to go through all the edges before you can say you're done. So this is why the complexity is that high. Okay. So minimum spanning tree has many applications. If you are designing a network, right, either a communication network or transportation network, right? So think of a case where you're building a new city or you're populating an island, right? So you need to sort of decide, okay, I need to construct roads. How do I do this, right? Because I need to be able to connect every place where people may need to live and work, but I don't want to do a connect every place to every other place, right? You just need to be able to get from one place to another, which means that at a minimum you need a spanning tree, right? So your minimum spanning tree formulation means, well, you have points and you have distances between them, right? So you could, in principle, construct a road between any 2 points, but you want to pick those particular set of roads such that the total cost of construction is minimized. So you can say the distance decides the cost. The distance between 2 points decides the weight of the edge between those 2 points, and now you go back and construct the minimum spanning tree. That would give you essentially the lowest cost way to build roads such that you can go from any place to any other place, right? And that is applicable, and you can generalize that to communication networks, electrical grid, various types of pipelines, and so on. Okay, and you can also apply this to clustering problems where you have a collection of points in a let's say two-dimensional space for simplicity, and now you're asked to cluster them. And once again, you can view that as a spanning forest construction because you don't have to necessarily connect everything together. You just want to form clusters. And once again, You might do that. For instance, let's say you form clusters where you're going to run buses between those, inside those clusters, and then maybe you have flights in between, across different clusters. So then you would construct essentially some kind of a spanning forest. Okay. So we'll talk about this. We'll stop here and pick up in the next lecture.